COMSOL allows us to extract the cross-section of a 3D geometry and run a 2D analysis, significantly reducing computational cost while maintaining accuracy. Hello, I'm Armin. Welcome to my channel. In this tutorial, I'll guide you through the process of extracting a cross-section and performing a stress analysis in COMSOL. Let's get started. I've already prepared the 3D model, so let's take a look at it. This is an optional sample, and I have imported it into COMSOL for this video. The material of the model is structural steel, and we are using the solid mechanics physics interface. The ring at the base is fixed, and a distributed load is applied on the top surface. I have chosen a finer mesh, which is suitable for our simulation, and I am using a stationary study. As you can see, the stress plot is already available. Let's start the modeling. First, we need to add a plane in the middle of the surface so that we can extract a cross-section and import it into a 2D component. To do this, we need to define the 2D component first. Currently, we only have a 3D component because the geometry is three-dimensional. We can right-click on the root node of the model and select Add Component 2D, or alternatively, we can go to the Model menu and add a 2D component from there. For simplicity, let's change the units to millimeters. Now the 2D component is ready to use. Let's start by creating a work plane at the middle of our geometry. Go back to Geometry 1, which belongs to the 3D component. Right-click on Geometry and select Work Plane from the menu. By default, the work plane is positioned in the middle of the geometry, so no adjustments are necessary. Next, switch to Geometry 2, the 2D component. Right-click on Geometry 2 and choose Cross-Section. Since there is only one work plane in Geometry 1, Work Plane 1 is automatically selected for the cross-section. Now simply click Build All Objects, and there you have it. The cross-section of our geometry is generated. Now let's assign a material to the 2D component. One way is to right-click on Materials and select Add Material from Library. However, a faster method is to copy the material from the 3D component. Right-click on Structural Steel in the 3D component, select Copy, then paste it into the materials of the 2D component. The material is now assigned and ready to use. Currently, Component 2 has no physics interfaces. To add one, right-click on Component 2 and select Add Physics. In the Add Physics window, expand Structural Mechanics, select Solid Mechanics, click Add to Component 2, and then close the window. Now it's time to define the boundary conditions, just like in the 3D model. First, let's fix the interior ring area. Right-click on Solid Mechanics 2 and select Fixed Constraint from the menu. Then select the inner circle of the geometry. Once the boundary condition is applied, you'll notice that the 2D model now mirrors the 3D setup closely. Next, we need to apply a distributed load. Right-click on Solid Mechanics 2 and select Boundary Load. Then choose the upper side of the sample. In the settings, change the load type to Total Force and enter -30 newtons, matching the 3D model setup. Now let's take a look at Mesh 2. To maintain consistency, we need to adjust it to match Mesh 1. Checking Mesh 1, it is set to Finer Element Size. So in Mesh 2, specify a finer element size and click Build All. Let's compare the two meshes. Change the view to the XY plane in the graphics window and rebuild Mesh 1. Here we can see the 3D mesh, and this is the 2D mesh. As you can see, both meshes are now similar. We don't need to create a new study because Study 1 is used for both components. Let's collapse Component 2 and Component 1. As you can see, Study 1 is positioned outside of the components, making it accessible for both. Everything looks good so far. Now, let's take a closer look at Study 1. Click on Study 1 Stationary. In the Physics and Variables section, we can see that both components are enabled. Expanding the mesh selection, you'll notice that both meshes are included in this study. Before solving the model, we need to clear the previous dataset. Expand Dataset, right-click on Study 1 Solution 1, and select Delete. This removes all previous results from the model. Before solving the model, we need to adjust the 2D approximation. Expand Component 2 and select Solid Mechanics. Since this is a thin structure, we'll use plane stress for the 2D model. The thickness is set to 3 mm, ensuring consistency with the 3D geometry. Go back to Study 1 and click Compute. Once the solution is complete, you'll see two solutions in the dataset, the first for 3D stress and the second for 2D stress. To compare 2D and 3D stress, it's helpful to enable the Show Maximum and Minimum Values box for both models. Expand the stress node, select Volume 1, and in the Expression section, change the unit to megapascal using the drop-down menu. Repeat this for the 2D model by selecting Surface 1 and setting the unit to megapascal. Now we can compare the stress results. As you can see, the 2D and 3D stress distributions are identical. This demonstrates that for thin structures, using a 2D plane stress model is not only accurate but also computationally efficient. The tutorial ends here. Let's quickly recap what we covered. In this tutorial, we converted a 3D COMSOL model into a 2D cross-section and performed a stress analysis. For this thin geometry, we used plane stress. After computing the solution, both the 3D and 2D models showed identical stress results of 151 megapascals. Thanks for watching, and I hope you found this tutorial helpful.